Alright, this is the second in our series of videos on matrix transformations. So in this video we're going to concentrate on, well, matrix transformations of the plane, meaning that we're only going to look at the case of transformations going from R2 to R2. So that means we're looking at matrix transformations of the form T of x equals A times x, where A here is going to be a 2 by 2 matrix. So the reason that to concentrate on the case of transformations of the plane is that we can actually visualize things a little bit better. Now, to kind of get us started here, let's think about a general 2 by 2 matrix, A, B, C, D, define our matrix transformation in terms of A, and let's think about what happens to these four vectors under this transformation. Now you may be wondering, why do we care about those four vectors? Well, the reason we care about those four vectors is that those four vectors, they represent the four corners of the so-called unit square. 0, 0, 1, 0, 0, 1, 1, 1. And so if we want to understand a matrix transformation visually, it's often useful to think about what happens to this little square in the plane. If we understand what happens to that square, we can understand a little bit better what happens to vectors generally, and we can get a nice visual picture. Now, one of the things you might want to do here is you might want to note that, well, the two of the four sides of that square, this guy and this guy, those are just your basic unit vectors in the plane, I and j. Of course, this corner here is just the 0 vector. The far corner, well, we know that that's I plus j. Now, we know from what we worked on before, we know that t of the 0 vector is always the 0 vector. We know that that stays put. What happens when I put in 1, 0? Well, let's actually work that out. A, B, C, D times 1, 0. I get A times 1 plus B times 0. I just get A. Then C times 1 plus D times 0. I get C. I get, you might have guessed this, I get the first column of A. And you can probably guess, if you haven't already, what happens when I plug in 0, 1. When I plug in 0, 1, I get the second column. Okay, so there's the second column. Now, as for the far corner of that square, 1, 1, recall that one of the things we can do with a matrix transformation is it distributes over sums. So T of I plus j is T of I plus T of j. So if I add those two together, I'm going to get A plus B, and I'm going to get C plus D, right? So notice that the if I want to visualize this, once I know where T of I and T of j go, I can add them together to figure out where the far corner goes. So what ends up happening is T of I ends up, and the actual location of these guys can be pretty unpredictable, but maybe there's T of I there, and maybe T of j ends up, maybe it's there, okay, and for T of I plus j, we can do our parallelogram trick. We know it ends up over there. That's T of I plus j, which is T of I plus T of j. Okay. And so what we end up with is something that looks like that. So our little square that we had gets transformed into a parallelogram. And of course, the exact details of what happens are going to depend on the numbers, right? If maybe maybe we might not even get a parallelogram. Maybe T of I is parallel to T of j, and everything just collapses down to a line. Maybe this thing gets flipped. Maybe it gets rotated. Maybe it's bigger. Maybe it's smaller. There's lots of possibilities that can happen here if we want to look at a general transformation. So this drawing is not representative of every possible transformation, but it does represent one possibility. To look at another possibility, let's try an example with concrete numbers. So let's plug in some numbers. We'll let t of x equal to a times x, right? So we know that t of I is going to be 1, 3. We know that t of j is going to be minus 1, 4, right? Plugging in 1, 0 gives me the first column. Plugging in 0, 1 gives me the second column. And if I wanted to kind of sketch things out here, in this case, we put in our little unit square. Here's I. Here's j. So t of I, well, 1, 3, so I go over 1, up 1, 2, 3 is going to be there. Okay. There's t of I. T of j, I go 1 to the left and up 1, 2, 3, 4. There's t of j. And for the sum, well, we know how to do that. We add these guys up, and we get this guy here. And there's t of I plus j, right? So t of I plus j, we know that's t of I plus t of j. So that's 1, 3 plus minus 1, 4. I get the vector 0, 7. And you can check that that's the same thing that I would have got if I had started with 1 minus 1, 3, 4, and then multiplied by the vector 1, 1. Okay. So in this case, we can see that our little unit square, it grew quite a bit. But you can sort of see how the transformation goes. You can imagine sort of grabbing this corner and stretching it up until it reaches that far tip up there, and if everything else kind of stays if everything that's currently a straight line remains as a straight line, and everything transforms proportionally, when I stretch that far corner up, I'm going to get that parallelogram. Okay, here's one more example. We've got a few particular vectors here. We just want to see what happens to those when we transform them. So we can calculate t of x, 1, minus 2, minus 2, 4, minus 1, 1. Now this one's a little interesting. What happens here? I get, let's see, minus 1, minus 2. I get minus 3, and then I get 2, and then I get 2 plus 4, I get 6. Okay. What about t of y? Let's just do the other ones quickly. T of y, I'm going to get, well, it's just going to be 2 times the first column. I'm going to get 2. I'm going to get minus 4. T of z, let me throw that one up here. I'm going to get 3 times 1, that's 3, minus 2 gives me a 1. 3 times 2 is minus 6, and then I'm adding 4, I get minus 2. One of the things you might notice here is that all of these guys are parallel. So notice that in this case, t of x is minus 3 times t of z, and t of y is equal to 2 times t of z. And what's interesting is we also know from the linearity properties here, we know that scalars can move in or out. So this is the same thing as t of minus 3z. This is the same thing as t of 2z, right? But what's minus 3z? Minus 3z is, that's minus 9 minus 3. And and what's 2 times z? 2 times z is 6, 2, right? all of these come out to be the same thing. So t of x, this minus 3, 6, I would get the same thing if I, so here I'm plugging in minus 1, 1. I would get the same thing if I plugged in the vector minus 9, minus 3. This vector here, 2 minus 4 for t of y, I would get the same thing. Instead of plugging in 2, 0, if I plugged in 6, 2, I would get exactly the same thing. Okay, so that's quite interesting. What happens, if we tried to sketch things? I'm not going to sketch them all, but let's sketch a couple of them. So where's x? X is here. Y is there. Z is there. And where's t of x? T of x is going to be kind of minus 3 up 6. T of x is going to be kind of around here. Okay, t of y over 2 down minus 4. T of y is kind of down here. T of z is half as long as t of y. T of z is sitting there, right? So the output, in this case, the output is always a multiple of this vector 1 minus 2. Now, you might notice that, we can guess why, right? Why is this happening? This is happening because this guy here, the vector minus 2, 4, well, that's minus 2 times the vector 1 minus 2, which is the first column. So the second column of my matrix is a multiple of the first column. The two columns as vectors, the two columns are parallel, and so we know that if I was doing, in general, if I was doing a times x1 x2, I would be getting x1 times 1 minus 2 plus x2 times minus 2 4, right? But that's going to be the same thing, since this guy here, this is minus 2x2 times 1 minus 2. I get x1 minus 2x2 times the vector 1 minus 2, right? So everything is parallel to that vector 1 and minus 2. The other thing you might notice is that from here's my coefficient. So, if x1 is equal to 2x2, then I get 0. So there are lots of, in fact, we know that the 0 vector goes to the 0 vector, but in this case there are actually lots of non-zero vectors that also go to the 0 vector. So, just as an example, a of 2, 1 gives me the 0 vector. We'll discuss later on that there are some connections here. If you have non-zero vectors that get sent to the 0 vector, that's basically your clue that something like this is going to happen, where the output of your matrix transformation, instead of giving you that nice parallelogram that we saw in the previous example, everything just collapses to lie along the same line. So in this case, if you want to think in terms of, say, the range, right? The range of this as a function is only vectors that are parallel to this guy, 1 and minus 2. Right? So the range ends up being a line through the origin. The range is one-dimensional, whereas in the previous example, the range is two-dimensional. And this is, so the fact that in this case there's a non-zero vector that gets sent to 0, that is actually not a coincidence, and we'll talk about that later. Okay, now, we saw in the last few examples that if you know the matrix, then it's easy to calculate t, the value of t on both 1, 0 and 0, 1, because those are just the columns of your matrix. Well, you can reverse this process, right? We know that if t of x is equal to a, b, c, d, times x, then we know that t of 1, 0 is a c, which in this case has to be this vector 3 and minus 1. We know that t of 0, 1 is b, d, and in this case we're told that that is the vector minus 2 and 4. And so now we know what A is, right? So if this is my matrix A, then A is going to be 3 minus 1 minus 2, 4, right? So knowing the value of our matrix transformation on just those two vectors completely determines its value on every other vector. But that's not so surprising from the properties of matrix transformations, right? It's not surprising that those two vectors are all we need, because if I wanted to do sort of t of xy, right, I can think of that as, so x times I plus y times j, and now I use the fact that I can distribute that across the sum. X and y are scalars. I can pull it out. I get x times t of I plus y times t of j, right? So as soon as I know these two values, the value of t on I and j, I know the value of t on every single vector, because I can always form this linear combination. So there are two ways that you can compute. If you have another vector that you want to compute the value of t on, either you can, if you know the value on 1, 0 and 0, 1, you can reconstruct the matrix and you can use the matrix to calculate the value of t on some other vector, or you can appeal directly to the properties. You can simply push t through as we've done here and calculate it that way. So for example, if I wanted to do t of 2, 3, I would get 2 times t of I, which is 3 minus 1, and then 3 times t of j minus 2, 4, and then I can simplify that. And what do I get in this case? 0 and 10. Okay, now there are a number of sort of common transformations of the plane that are sort of geometric. They're easy to understand. These are ones that that you may have run into in the past, but you probably ran into these in the context of graphs, transforming graphs, reflecting a graph across an axis, rotating, stretching, shrinking. The one that we don't look at here is translations. We don't look at translations because translations do not preserve the origin, so they're not a linear transformation in the sense that we consider, right? So there are a number of reflections that we can consider depending on how you want to reflect. So for reflections, we can think about ones that go across the x-axis, across the y-axis, or even across the origin. Rotation by some angle of, say, theta, stretches, shrinks. There are a number of transformations that you can do. So if I want to think about, for example, let's say I want to reflect across the x-axis. Okay. So what does that look like? If I think about it in terms of points, right? If I have a point up here, xy, and I reflect across the x-axis, right? So I'm constructing the mirror image on the other side of the x-axis from that point. Well, the x-coordinate remains unchanged. The y-coordinate is now the opposite sign of what it was before, right? It's the same distance away from the x-axis, but on the other side. So you can think about that in terms of, you can think about it two ways. You can think about it like this. You can think about it as, t. So think of these guys at those points as vectors. Then what this says is that t of xy should be x and minus y, right? And so I want to write that down as a matrix. So what should the matrix be? Well, what happens to 1, 0? Nothing happens to 1, 0. T of 0, 1. well, that's going to become 0 and minus 1, right? But we can see that if we, if you draw those guys in, right, I, j, right? So if I reflect I, nothing happens because it's already on the x-axis. It's got nowhere to go. But this guy, if I reflect, well, it's going to get flipped over. T of j is down here, right? But now I know what my matrix should be because I know that the values of t on these two vectors give me the columns of my matrix. I get 1, 0, 0, minus 1 times xy, right? And every other transformation can be figured out in a similar way. The only one that it takes a little bit of work, it takes a little bit of trig knowledge to figure out is the rotation. If I start with a vector v, t of v is here, and if t of v is obtained by simply rotating through an angle of theta, then it turns out that t of v, the matrix for this rotation, is cos theta and then minus sine theta, and cos theta. Well, times v. Maybe I should just simply say that the matrix in this case is given by that. So this rotation matrix, this works whatever the angle theta happens to be. If you're dealing with a rotation through an angle of theta, a matrix of this form will do the job for you. So you'll see a few of those pop up in the examples in the textbook. All right. So here's an example. Here's a common example thinking about transformations of the plane. Now a general transformation of the plane might be formed by doing several of these basic transformations in some sort of order. Okay, so we want to think about it this way. We start with so think about doing kind of a general. There's a couple ways to do it, but think about doing a general vector. So I start with some v, right, and v is going to go first, so first we're going to stretch, right? And so I'm going to apply a stretch transformation. I'm going to call that T1, okay? So I get a T1V, okay? Then I'm going to rotate, right? So what am I rotating? I'm not rotating the original vector. I'm rotating the one that I've already stretched. So I've got a new function T2. And what do I plug into T2? I put in T1. Okay. And then I'm going to reflect. And so when I reflect, I've got a new function. I've got a function T3 that does the reflection for me. And what do I plug in? Well, I plug in this guy here, the one that's already been rotated and stretched. So T3, T2 of T1 of V. And here we see that we have this function composition going on. Now we want to think about this in terms of a matrix, right? So T1V, this has to be given by A1 times my vector V, right? And now T2, that's given by multiplying by some matrix A2, right? But I'm multiplying, the input always goes on the right, so it's A2 times A1 times V. And then similarly here I have A3 times A2 times A1 times V. Okay? And so this guy here is, I could write this as simply A times V, where A is A3, A2, A1, right? Be careful of the order. Notice it goes 3, 2, 1. It doesn't go 1, 2, 3, and that's simply because the input always goes on the right. And so when you apply, each time you apply a new function, that function is applied to the left of what you already have. So how do we do a vertical stretch? What does a vertical stretch look like? Well, a vertical stretch means that you're leaving this guy alone, right? So I doesn't have any vertical component to it, so it gets left alone. J, on the other hand, gets stretched up by a factor of 4, right? So T of J is here. So what does A1 look like? A1 must look like, well, nothing happens to I, but J gets multiplied by 4. So my vertical stretch looks like that, 1, 0, 0, 4, right? We're multiplying the Y value but not the X value. That rotation through an angle of pi over 3, A2, if I use the formula I had before, that's cos pi over 3 minus sine pi over 3, sine pi over 3, cos pi over 3, and so that is going to be 1/2 minus root 3 over 2, root 3 over 2, and 1/2. A3. A3 is a reflection across the y-axis. Let me just hop back for a second. If I were to reflect across the y-axis instead of the x-axis, that would mean reflecting this way. That would mean changing the sign of the x-coordinate instead of the y-coordinate. So instead of having a -1 down here, I would have a -1. So this, instead of this -1, I would put a -1 there, so the x gets multiplied. So I get -1, 0, 0, 1. Okay, so my matrix T. Oh, you guys again. Alright, so T of x is equal to A times x, where A is just this product. So I'd have to do A3 times A2 times A1. Multiply those three guys together, and that would give me my, my matrix. Okay.